Yesterday we learned that the indefinite integral f of x dx equals some function capital F of x means that the derivative of capital F of x equals little f of x. In other words, we're given the derivative. And we want to find the original function. Instead of being given a function and you want to take its derivative, we're given the derivative. We want to undo those derivative shortcuts and get back to our original function. We can always check our work on antidifferentiation by taking the derivative of what we think our answer is for the antiderivative and making sure we get the original function. This is called an indefinite integral, and it means the most general antiderivative. Why? What's this business about most general antiderivative? Well, the answer to an indefinite integral always involves a plus c. Because if you give me one antiderivative, I can find another one just by adding a constant to it. Because the derivative of a constant is 0. So really an indefinite integral is a family of functions. Okay? Now, for every derivative shortcut, there's a rule or a technique to undo that shortcut and get back the original function. This is what we mean by the topic techniques of integration. And in Chapter 5, we're learning a couple of techniques of integration. In Calculus 2, you learn many more techniques of integration. That's at least a third of the course. 3 comments. Why this symbol for the most general antiderivative of a function? Well, it's because we're going to next week learn what this definite integral means. This is a definite integral. And we'll learn what that means. And we'll learn the connection between the definite integral and the indefinite integral. And this symbol will be very apparent to us next week why we choose that for a definite integral. Again, you don't know what a definite integral is yet. That's in next week's topic. But it'll be apparent why this is a good choice of symbol for a definite integral. And then you'll see that we're just borrowing the notation for an indefinite integral. Okay? This may not make sense to you. I'm just trying to explain why this kind of weird symbol is being used for the most general antiderivative of this. It's because this symbol makes sense in a different context, and you'll see that later, and we're just stealing the symbolism for this context. And you'll see why that might make sense to do that. Okay? It is important to write this little dx. What's the meaning of that dx? Right now it has and it should have no meaning to you. Okay? It's just a symbol. It's kind of like if you write a, you know, is that a minus sign in the a? Well, it looks like it, but it doesn't mean minus, right? It's just part of the symbol for a. Well, right now what you need to think of is that this dx is glued to this curly Q, okay? And that's just the symbol for the most general antiderivative of the function that goes here. Okay. Another comment, can you use power rule for antiderivatives on this function? Remember, power rule on the most general antiderivative of x to the negative 1. Power rule, remember, for antiderivatives says you add 1 to the exponent and you divide that. Well, if you add 1 to the exponent and divide, you are dividing by 0, and that's undefined, right? So can you use power rule for antiderivatives for this function? No. But, so that tells me, when we stated power rule yesterday, I really should have said it works for every real number power except for negative 1. I forgot to say that. But x to the negative 1 is what? It's 1 over x. And you know the derivative of the natural log of x is 1 over x. So we just need to remember that, right? Most general antiderivative of x to the negative 1 is the most general antiderivative of 1 over x. And that's natural log absolute value of x plus c. Again, we could talk more later about why you want these absolute values. Certainly you cannot take the natural log of a negative, and this is emphasizing that. But there's another reason also why you want the absolute values. Right now, just remember, put the absolute values around the x. And the last thing I need to point out is, I've asked you to read in the last lesson, section 4.9. Read all of that. It talks about finding antiderivatives and the most general antiderivative, but it doesn't use the indefinite integral symbol. In 5.4, they do exactly the same thing as in 4.9, only they introduce the indefinite integral symbol. Okay, so I've just combined those two sections. But don't read all of 5.4. 5.4, just read through example 2. The reason is the rest of that section talks about definite integrals, and it assumes that you have done sections 5.1 and 5.2 and 5.3. And we haven't done those yet. We're going to do those after we finish 5.4. I think this is just, or finish indefinite integrals, part of 5.4. I think this is just a more logical order in which to do things. Plus, seems to me like it makes sense to do all the anti-differentiation stuff right after the derivatives, and then go to the new topic of definite integrals, which is a different topic, and then see how definite and indefinite integrals are connected. And then also, I'm trying to get the most important material out there first.